Hey everyone, and welcome to section 3.6. In this section, we're going to be looking at graphs of functions and how to determine, if I have a graph of a relation, how will I know if it's a function, and what are some graphs of common functions I should be aware of. So, let's recall, for a linear equation ax plus by equals c, which we've worked a lot with, the graph of that equation is the set of points that are solutions to the equation. And being a set of ordered pairs or points in the plane, it's a relation. So I know that the equation defines a relation, but does it define a function? And we looked at some basic examples in the last video about determining whether an algebraic equation represented a function, but it's not always super easy to tell just by looking. But if I have the graph, it becomes very easy to tell whether or not a relation is a function. So what we have is the following result. This is a way of testing whether or not a graph you have represents a function. So a set of points in the plane defines y as a function of x, or y equals f of x, if every vertical line intersects the set in at most one place. This is the so-called vertical line test. So here we have a graph of a relation, and I'm going to use the vertical line test. So you see that no matter where I draw my vertical lines, the orange lines will only intersect this yellow curve at one point. What about something like a circle? Well, it's possible that you have vertical lines that don't even pass through your graphed relation, but to be a function is somewhat strict because it's saying that every single vertical line that I draw intersects the set in at most one place, which means if I can find one vertical line that intersects the graph more than once, then the graph is not a function. And we see here for this circle that we have vertical lines that intersect the graph in two places. So this first guy was a function. This second one is not. Here's another example, and I just want to look at vertical lines. And again, for this guy, it doesn't matter where I put the vertical lines. They are only intersecting the yellow curve in one place. So this picture is the graph of a function. All right, and then this last picture, if I start drawing my vertical lines, and notice I can find vertical lines that intersect the yellow set in more than one place. So, not a function. All right, so that's the vertical line test. It's a super easy way to check if a relation that you have graphed is a function of x or not. And so if y is a function of x, or in other words, y equals f of x, then the graph of the function f of x is the set of all ordered pairs x comma f of x, where x is a member of the domain. So again, if we're thinking of this in terms of inputs and outputs, then on one axis, the x-axis, I am placing my input, and then on the other axis, I am seeing my outputs. Okay, so again, f is the name of the function, x is the x-coordinate of a point in the graph of f, and f of x is the y-coordinate of a point in the graph of f. So when I talk about a function as an object, I'm going to use, for example, f. But if I want to talk about specifically the y coordinates of that function, I'm going to say f of x. So this is a common way to write it. If I graph a function, then you draw the curve on the plane, or whatever it is, and you write y equals f of x, except you're substituting whatever f of x actually is. So let's look at some of the functions that we're most likely to see. First up is one that's very familiar to us, and those are the linear functions. So these are functions of the form f of x equals mx plus b, where m, we know, is the slope and b is the y-intercept. So the graphs of these functions are lines. And I want to draw your attention to the domain and range for a second. The domain and range of a linear function consists of all of the real numbers. So I can plug any number in I want for x, and I can get any number out that I want as well. So the domain and range are everything. All right, next up we have a constant function, which is just a flat horizontal line, and it looks like f of x equals c, where c is some real number. So these are not terribly exciting functions because they don't even have x's. So if you try to plug in an x, there's nothing to even plug the x into, so to speak. So just for that reason alone, the domain of this function would be all real numbers. The range, however, notice that since the line is completely flat, it's not going up or down. So there's really only one value that you're getting from a constant function, and it's whatever this number c is. All right, so here we have the identity function, f of x equals x. This is simply whatever you put in, you get out. So if I feed 1 into this function, f of 1 would still be 1. So this is a line that makes a 45-degree angle with the x-axis. It moves up and down in equal ratio, and you can kind of think of this in terms of linear functions. It's a linear function where the slope is 1 and the y-intercept is 0. Again here, the domain and range are going to be all of the real numbers, because there's nothing wrong with entering any real number here for x. There's no restrictions. Next up we have the square function, or f of x equals x squared. So again, my x and y-intercept are 0, and any real number that I can imagine, I can square, right? It doesn't matter if a number is negative or positive or 0 or anything. I can square any number. So the domain is all real numbers, but the range is the interval from 0 closed to infinity. So what does this mean? This means we can't square a real number and get a negative number. So all of the negative numbers are excluded from the range of this function. Next up is the cube function, f of x equals x cubed. 0 is both the x and y-intercept of this guy, and unlike the square function, I can plug in any x value I want and get out any x value I want, negative or positive. So both the domain and range are all real numbers. Next I have the square root function. So even though its intercepts are 0 and 0, the domain and range are different. So why are the domain and range 0 to infinity and they're not negative infinity to infinity like some of the other ones. So let's look at the range first. Remember from an earlier slide that this symbol has a special meaning. It's the principal square root, or the positive one. So when I feed a number into the square root, I'm getting a positive or 0 number back. So that's why the range only consists of non-negative numbers. And the domain is 0 to infinity, just for the fact that we can't take square roots of negative numbers, right? If I had -1 under the square root, I would need to have a number that when squared gives me -1. And there is no such real number. And last up, we have the absolute value function. F of x equals absolute value of x. The x and y intercept here are 0. And the domain and range are -infinity to infinity for the domain and 0 to infinity for the range. I can plug in any number into an absolute value, but I only get numbers that are greater than or equal to 0. So if I look at the graph of the identity function again, you'll see that the absolute value function modifies the identity function by just taking this bottom left part of the line and flipping it over the x-axis, resulting in that picture. And that makes sense. When we take the absolute value of a negative number, we get a positive number. So it makes sense that only the output should only either be 0 or positive. And that about does it for graphs of functions, which also brings us to the end of chapter 3. So moving on from here, we're going to be looking at systems of linear equations. We're going to be skipping several sections in that chapter, mostly the later ones. So we're really only doing like the first 2.5 sections of that chapter. So stay tuned.